You wake up in the morning, sit on the edge of the bed, and slowly place your feet on the floor. The moment your feet make contact, you feel something familiar: your weight. Your ankles adjust, your knees respond, the muscles in your legs quietly tense to keep you upright. Beneath your feet, the floor pushes back against you with exactly the kind of resistance you have felt thousands of times before. Nothing about it seems strange. You stand up. Your body settles into balance. You take a step. The floor remains beneath you, supporting every movement, while something seems to be pulling your entire body downward. You have probably never stopped to separate those two experiences. You simply call the sensation gravity, but there is something remarkable hiding inside this ordinary moment. What you feel in your feet is not a direct sensation of some invisible force reaching through space and grabbing you. Your body is responding to pressure, contact, and the resistance of the ground beneath you. And that distinction matters, because the way gravity feels is not necessarily the same as what gravity actually is. Right now, standing on the floor, you may imagine yourself being pulled downward through space. But there is another way to describe what is happening, one that makes the floor beneath your feet suddenly far more important than you might expect. The ground is not merely sitting underneath you. In a deeper description of nature, your body is being prevented from following the path it would otherwise take through space-time. That sounds abstract, but the sensation in your feet is completely real. The pressure is real. Your weight is real. Your balance is real. What may be wrong is the picture you have carried in your mind for years about why you experience them. And once you separate what your body feels from what physics says is actually happening, an entirely different question begins to appear. If gravity is not quite the kind of force you have always imagined, then what is actually pulling you toward the ground? Why does an apple fall? Why does the moon continue circling Earth instead of flying away? Why does Earth remain in orbit around the sun? And perhaps most strangely of all, why do you feel your own weight when you are simply standing still? The obvious answer seems to be that something is pulling on everything around you, an invisible rope, stretching from Earth to your body. But that picture is misleading. Gravity is not simply a stronger version of magnetism, either. Magnetism can push and pull certain charged materials. Gravity behaves differently. It acts on mass energy itself, and there is no ordinary gravity substance flowing invisibly through the room and grabbing objects. So you might hear the phrase, "Space is curved," but even that can become meaningless if you simply memorize the words. Curved into what? Curved how? And why would a curve in something you cannot even see make your feet press against the floor? Here is where the mystery becomes much more interesting. You do not need a laboratory to look for the evidence. It is already surrounding you. Look at the floor beneath your feet. Look at an object that could fall from a table. Look at a clock measuring the passage of time. Look at a beam of light traveling across a room. Even the cabinet, the wall, or the table beside you is quietly participating in the same structure of reality. These ordinary things are not separate from the mystery. They are the mystery. The deeper question is not simply, why does gravity pull things down? It is more fundamental than that. Why does matter follow the paths it does in the first place? And before we go any further, there is something important to be honest about, because the phrase, gravity isn't a force, is often presented in a way that creates more confusion than understanding. There is a problem with the way gravity is often explained online. You may hear dramatic claims like, gravity isn't real, or gravity doesn't exist, or even, Einstein proved Newton was wrong. Those statements make excellent headlines. They also leave out the part that actually matters. Newton was not simply wrong. In fact, Newton's description of gravity remains extraordinarily useful. Engineers use Newtonian mechanics to calculate trajectories. Astronomers can predict many planetary motions with remarkable accuracy. You can design machines, bridges, satellites, and countless other systems without solving Einstein's equations every time gravity enters the picture. So why did Einstein need a different theory? Because eventually, the simple picture of gravity as a force acting between masses runs into situations where it is not the deepest description of what nature is doing. Newton gave us a powerful rule for calculating gravitational effects. Einstein went further and asked what gravity actually means as part of the structure of the universe. That distinction is important. Imagine having a map that tells you exactly how to get from one town to another. The map can be extraordinarily accurate and useful, but that does not mean it contains every detail about the landscape underneath it. In much the same way, Newtonian gravity can give you the right answer without revealing the deeper geometry behind that answer. General relativity does not simply erase Newton's theory. It explains why Newton's approximation works so well when gravitational fields are relatively weak and speeds are far below the speed of light, and then it extends the picture. In Einstein's description, gravity is intimately connected with space-time itself, the combined structure of space and time. Matter and energy affect that structure, and freely moving objects follow paths determined by it. That is much more precise than saying gravity isn't real. Gravity is real enough to keep your feet on the ground. What changes is our understanding of what produces the experience we call gravity. So this is not a story about one genius destroying another genius's theory. It is a story about a successful description being replaced, in deeper circumstances, by a more comprehensive one. And that difference is where the real strangeness begins. So rather than throwing away everything you learned about gravity, we're going to keep the useful part and then look underneath it. This is where we try to slow things down. Not because the science needs to be made simpler than it really is, but because complicated ideas become much more interesting when you can actually see the reasoning that connects one step to the next. You do not need to memorize Einstein's equations. You do not need to accept a strange statement simply because a famous physicist said it. And you certainly do not need to replace one slogan with another. The goal here is different. We want to follow the mechanism. We want to understand why an idea that initially sounds impossible can eventually become almost unavoidable once you see the pieces connected together. Because the most fascinating part of physics is rarely the final sentence. It is the chain of reasoning that gets you there. So stay with this for a few more minutes. Now let's start where the mystery becomes physical, with the path an object takes when nothing is pushing it. Start with the picture you already know. Drop a ball from your hand and it accelerates toward the ground. Near Earth's surface, that acceleration is approximately 9.8 meters per second squared. Newton's framework describes this beautifully. Earth has mass. The ball has mass. Gravity acts between them, producing the downward acceleration we observe. If you want to calculate how long the ball takes to reach the ground, how a projectile travels, or how a planet moves through space, Newton's equations can give you remarkably accurate answers, and that is precisely why Newton's description survived for centuries. But Newton's theory tells you how to calculate the gravitational interaction. It does not fully explain what gravity means as part of the structure of space and time. That deeper question leads to Einstein. One of Einstein's most important clues came from a deceptively simple thought experiment. Imagine yourself inside a sealed elevator. Suddenly, the elevator begins accelerating upward. You feel yourself pressed toward the floor. Objects released from your hand appear to fall toward the floor. Now imagine that instead of being inside an accelerating elevator, you are standing inside a room on Earth. From your local perspective, the two situations can look remarkably similar. That was the key. Locally, acceleration and gravity can produce effects that are indistinguishable. But now reverse the experiment. Imagine cutting the cable of the elevator and allowing it to fall freely. You and everything around you fall together. For a moment, the pressure disappears. You become weightless. That is the strange clue. The person standing on Earth feels weight. The person falling freely toward Earth does not experience that same weight. So perhaps free fall is not the abnormal situation. Perhaps it is the natural one. This becomes much easier to see if you think about astronauts orbiting Earth. The International Space Station is not beyond Earth's gravity. Earth is still pulling on it. Its orbital speed is roughly 7.7 kilometers per second. But the station is moving sideways so quickly that as it falls toward Earth, the surface curves away beneath it. It keeps falling and keeps missing the ground. That is an orbit. In this sense, an orbit is continuous free fall, and now we can return to you standing on the floor. You are not freely falling. The floor stops you. Your body would otherwise follow its natural free fall path, but the solid ground continually pushes upward against your feet. That contact force travels through your shoes, your feet, your ankles, your legs, and your skeleton. That pressure is what your body experiences as weight. This gives us a remarkable reversal. A person in free fall can feel almost weightless. A person standing still on Earth feels heavy. So the sensation we normally associate with gravity is actually telling us something about the ground preventing free fall. Now we need a deeper description of what that free fall path actually is. This is where space-time enters the picture. Einstein's general theory of relativity, published in its completed form in 1915, describes gravity not simply as an invisible force pulling objects through space, but as a consequence of the geometry of space-time. Matter and energy influence that geometry, and once space-time has that geometry, freely moving objects follow natural paths through it. These paths are called geodesics. A geodesic is the closest thing general relativity has to a straight line. But there is an important catch. A geodesic does not have to look like a straight line on an ordinary three-dimensional map. The geometry belongs to spacetime itself, including time. That is why simply imagining a rubber sheet sagging under a heavy bowling ball can be useful as a crude visualization, but it cannot capture the real theory. There is no need for an external downward direction into which spacetime must bend. The geometry is the thing, and that geometry affects motion. It affects the paths of falling objects. It affects the trajectories of planets and spacecraft. It even affects the passage of time. The speed of light in vacuum is exactly 299,792,458 meters per second, and light follows paths determined by spacetime geometry as well. In sufficiently strong gravitational fields, those paths can bend relative to what a distant observer might expect. We have experimental evidence that this is not philosophical wordplay. Gravitational time dilation has been measured. Clocks at different gravitational potentials tick at different rates, and modern satellite navigation systems, such as GPS, must account for relativistic effects to maintain accurate positioning. The same framework that explains why an object falls also tells us why clocks do not all experience time at exactly the same rate. That is the deeper connection. Gravity is not disappearing. The effects are not imaginary. What changes is our interpretation. The ground pushes you away from free fall. A freely falling object follows a natural path through curved spacetime, and what Newton called gravitational acceleration can emerge, in Einstein's deeper description, from the geometry of that spacetime. This is why the phrase, "gravity isn't really a force," needs careful handling. It does not mean gravity is fake. It means that in general relativity, the deepest description does not require a conventional force pulling a freely falling object away from its natural path. And this is where everyday intuition begins to betray us. Because what most people do when they think about gravity is almost the exact opposite of what the physics says. Think about what your mind automatically does when you hear the word gravity. You probably picture Earth pulling everything downward. You picture an invisible force reaching through space, constantly tugging on your body, your chair, your coffee cup, and everything else around you. It is an understandable picture. It is also the picture Newtonian physics gives us. The problem is that we often carry that picture into situations where it becomes misleading. Take an astronaut orbiting Earth. You might imagine the astronaut floating because Earth's gravity has somehow disappeared. But gravity has not disappeared. At the altitude of the International Space Station, Earth's gravitational influence is still very strong. The astronaut is floating because the astronaut and the spacecraft are both continuously falling. They are falling toward Earth while moving sideways fast enough to keep missing it. The astronaut experiences very little support force because there is no floor underneath them, constantly pushing them away from that free fall path. Now reverse the situation. You are standing on Earth. Your mind says, "I am at rest." But from the perspective of general relativity, that statement requires more care. You are not following the same natural free-fall trajectory that a freely falling object would follow. The ground is in the way. It pushes upward against your feet. That force travels through your body and creates the sensation you call weight. This is one of the strangest reversals in the entire subject. The person falling toward Earth can feel weightless. The person standing motionless on Earth feels heavy. So when you jump, something interesting happens. For a brief moment, the ground is no longer pushing upward on your feet. You enter free fall. You feel lighter because the contact force disappears. Then the ground catches you again. Your feet experience a sudden force. Your legs absorb it, and your body immediately recognizes the familiar sensation of weight. The same distinction appears when you sit in a chair. The chair pushes upward against your body. When you lie down, the mattress pushes against you over a larger area. When you walk, the ground continuously interacts with your feet and changes your motion. These ordinary experiences are not separate from the physics. They are examples of it. And this is where our intuition gets turned upside down. We tend to think, "I feel heavy because gravity is pulling me downward." But in the general relativistic picture, the sensation of weight comes from something more specific. You are being prevented from freely following the path dictated by the local space-time geometry. The ground is doing the pushing. That does not mean gravity has stopped mattering. Without Earth's mass and the resulting space-time geometry, there would be no reason for that particular free-fall trajectory to exist. But the sensation itself is produced by contact, so the distinction is not, gravity is real versus gravity is fake. The distinction is, A freely falling object follows its natural path. A supported object is forced away from that path. And once you see that, something familiar begins to look completely different. You were taught to associate falling with gravity and standing with rest. But physics gives us almost the opposite intuition. Falling is closer to natural motion. Standing on the ground requires a continuous physical interaction. And that raises an important question. If Newton's force picture works so extraordinarily well, why would physicists ever need this more complicated way of thinking about gravity? But if this interpretation is so different from what we were taught, why did the old picture work so well? And why do physicists still use the language of force? If you grew up learning that gravity is a force, then it is completely reasonable to wonder whether Einstein simply proved that Newton was wrong. But that is not what happened. Newton's law of universal gravitation was built from something remarkably powerful. Observation. Objects fell toward Earth. The moon moved around Earth. Planets followed predictable paths around the sun. Newton realized that these apparently different phenomena could be described by the same mathematical rule. That was an extraordinary achievement. For centuries, Newton's framework allowed scientists and engineers to calculate gravitational motion with astonishing success. The important point is that the equations did not suddenly become useless when Einstein arrived. They remained useful because, under many ordinary conditions, Newton's description is an extremely good approximation. The deeper problem was not accuracy in everyday situations, it was interpretation. In Newton's framework, gravity is treated as a force acting between masses. In general relativity, gravitational phenomena emerge from the geometry of spacetime. That is a fundamentally different picture of what is happening underneath the calculation. You can think of it this way. Newton tells you an exceptionally reliable rule for predicting what objects will do. Einstein asks what kind of universe makes that behavior happen, and his answer involves spacetime itself. The Einstein field equations express this relationship mathematically. Matter and energy are related to the geometry of spacetime, while that geometry determines the paths available to matter and light. This was not merely a beautiful idea. It made predictions. In 1919, observations of a solar eclipse provided evidence consistent with Einstein's prediction that the sun's gravity would deflect starlight passing near it. The result helped transform general relativity from a radical theoretical proposal into one of the most famous ideas in modern physics. And the story did not end there. Relativistic effects have since become part of practical technology. GPS satellites carry clocks whose rates differ from clocks on Earth's surface because of both their motion and their gravitational environment. Without accounting for these relativistic effects, satellite navigation would accumulate significant positioning errors. So this is not a choice between Newton and Einstein. You do not have to throw away everything you learned in school. Newton's theory remains extraordinarily useful within its domain. General relativity gives us a deeper framework that becomes essential when precision, strong gravitational fields, high velocities, or other relativistic effects matter. This is how science often advances. A newer theory does not necessarily destroy an older theory. Sometimes it explains why the older theory worked so well in the first place. Newton gave us the gravitational force. Einstein revealed a deeper geometric structure beneath many of the phenomena that force successfully described, and that should change the way you think about scientific progress. The question is not always which scientist was right. Sometimes the better question is, how much of reality does each description allow us to see? So you can keep Newton, you can understand Einstein, and you can recognize that the two descriptions belong to different levels of approximation and depth. So now that the mental picture has changed, the most useful thing is not another equation, it is knowing how to recognize this strange idea in the world around you. Now that the mental picture has changed, you can actually practice noticing it. You do not need a laboratory, a telescope, or a complicated equation. Start tomorrow morning. When you stand up, remain still for about 30 seconds. Pay attention to your feet. Notice the pressure beneath your heels and the balls of your feet. Notice how that pressure travels upward through your ankles, legs, and body. Do not simply think, gravity is pulling me down. Instead, notice what your body is physically detecting. The floor is pushing against you. That contact force is what gives you the familiar sensation of being supported, the sensation we call weight. Now, without doing anything dangerous, imagine the floor suddenly disappearing and you entering free fall. What would happen to that sensation? The supporting contact force would disappear. You and everything around you would accelerate together, and you would experience the kind of weightlessness astronauts experience in orbit. Next, find a small, lightweight object you can safely drop over a table or floor. Hold it roughly 30 to 50 centimeters above the surface and let it go. Watch what happens. But this time, try not to picture an invisible hand pulling the object downward. Instead, think about its path. The object is following a natural trajectory through spacetime. Then the floor interrupts that trajectory. The impact is where the freefall motion ends. That tiny everyday event is a miniature reminder of the much deeper principle. Now think about astronauts aboard the International Space Station. If you see footage of them floating around the station, remember that they are not floating because Earth's gravity has disappeared. The station is moving around Earth at roughly 7.7 kilometers per second. It is continuously falling toward Earth while moving sideways fast enough to keep missing it. The astronauts, the station, and everything inside are falling together. That is why they experience apparent weightlessness. Then consider something you probably never associate with gravity at all: a clock. General relativity predicts that clocks in different gravitational environments do not all tick at exactly the same rate. On Earth, the effect is extremely small in ordinary circumstances, but modern technology cannot simply ignore it. Satellite navigation systems such as GPS depend on relativistic corrections because the clocks aboard satellites experience both different gravitational conditions and different motion compared with clocks on Earth's surface. So relativity is not merely a philosophical idea about what gravity really means. Its predictions matter to technology you may use every day. And now keep two mental models in your mind. The first is Newton's. Gravity behaves like a force between masses, and this model provides extraordinarily accurate predictions in a huge range of ordinary situations. The second is Einstein's. Gravitational phenomena are fundamentally connected to the geometry of space-time, and freely falling objects follow natural paths through that geometry. You do not need to destroy the first model to understand the second. In fact, keeping both is more useful. One gives you a powerful approximation, the other reveals a deeper structure, and that may be the most practical lesson of all. The next time you stand, walk, sit, jump, watch something fall, or look at a satellite moving across the sky, you can ask yourself what your body or your intuition is telling you, and then ask what the deeper physical description says is actually happening. You do not need to memorize the Einstein field equations. You only need to notice the distinction. Standing is not free fall. Weight is not the same thing as gravitational motion, and the ordinary world around you is constantly giving you clues about the geometry of space-time. And tomorrow morning, when you stand up again, the same floor beneath your feet will be giving you a clue about one of the deepest ideas in modern physics. Tomorrow morning, you will stand on the same floor. Nothing about it will look different. Your feet will feel the same pressure. Your body will feel the same weight. But now you can recognize what that sensation is telling you. The ground is not simply holding you against an invisible downward pull. It is preventing your body from following its natural freefall path through space-time. The floor has not changed. Your understanding has. And every morning, for as long as you stand on Earth, you have another opportunity to notice the same quiet clue hiding beneath your feet. And once you begin seeing gravity this way, many other familiar things in the universe start looking completely different. If this kind of explanation is useful to you, consider staying with us. There are deeper mechanisms hiding behind many familiar things we experience every day. That is what this channel is built around, taking ordinary ideas apart, following the questions further, and revealing the physics underneath. Because sometimes, the strangest discoveries are hiding in the things we stopped questioning long ago.